After watching this video lecture, students will be able to identify specific characteristics of gases, as well as differentiate between real and ideal gases. So we're going to go ahead and discuss gas characteristics. The first thing to understand is that gases are going to uniformly fill any container that they are held in. That's going to be in contrast with solids and liquids. We know that solids are going to keep whatever form they have. They actually don't expand to fill the container. Liquids, on the other hand, are going to take the shape of the container, but they don't expand out and fill the entirety of the container. Because of this spacing that we see with our gases, we know that they can be compressed. You know, oxygen, acetylene, there's lots of gases that we maybe see in the shop or in the hospital, and that's taking advantage of the fact that the gas particles are so far apart that when we apply pressure, we can condense it down. Also, they mix completely with any other gases, so when you basically combine different gases, you're going to have an even distribution throughout the room or the container because the gases are going to mix completely. So that means that when we're sitting in a classroom or we're sitting somewhere, the air that we're breathing, right, the oxygen that exists in the air is distributed evenly throughout. That's why we can breathe in all parts of the classroom. Okay, gases also exert pressure on their surroundings. Okay, so if you look at, say, a balloon, that balloon is going to have particles of gas that are floating around, and those particles of gas are running into the sides of the balloon. These collisions then subsequently are exerting forces, which are the pressure that the gas is exerting on the surroundings. And this is also what gives your balloon its specific volume or shape. Gases, again, they mix completely, they diffuse into one another, they mix together. And gases, guys, can be described with respect to their volume, temperature, pressure, and specific quantity or amount present. We're going to take advantage of these components as we move into the calculation aspect of this unit. So as we're about to approach dealing with calculations based on gases, we need to first differentiate between ideal and real gases. Ideal gases are what we're going to assume that all gases behave as. Basically, ideal gases are these imaginary gases that follow these assumptions of kinetic molecular theory that we see down here in this area here. So the assumptions of kinetic molecular theory: all particles are in constant random motion. Gas particles don't take up volume, so we're saying that the molecules themselves don't have volume. Collisions are elastic, meaning that when a molecule bumps into, say, the side of a balloon or something, it returns in the other direction with the same energy. And the last thing is that we assume that the gases have no forces of attraction or repulsion. The gases not taking up volume and not having attractive forces are two of the most important assumptions for simplification of our calculation. So remember, ideal gases are imaginary gases that fit these assumptions. Of course, real gases are what we're actually dealing with, but again, for simplification, we're going to assume that all of the gases we deal with are ideal. So real gases do not behave according to kinetic molecular theory. Real gases are going to be attracted to each other. The particles have intermolecular forces, so that's going to affect things like pressure. They also have volume. The molecules themselves have shape and structure and take up actual space, so of course they have volume themselves, which of course would affect your volume components. And the collisions, are not perfectly elastic. Okay, there are energy changes and exchanges that are occurring as those particles float around. Now, the reason why we can assume that the gases we're dealing with, though, are going to behave ideally is because in most situations we're at, low-ish pressure and, relatively high-ish or, medium temperatures. The only time that we have to worry about real gases and the assumptions that we make about these gases being true is at high pressure and very low temperatures. At high pressure and low temperatures, the particle spacing is not as great for the gas. Also, you slow down those molecules, the intermolecular forces are going to start to come into effect more strongly. So basically, our gases that we're dealing with, we're just going to assume and pretend that they behave ideally, despite the fact that these gases, actually have volume and attractive forces. As long as we're not at high pressure and really low temperatures, the assumptions work and our calculations are simplified drastically.